Hello students, welcome. Today we will solve a question in multi-property problems. So let's see problem number 1. Evaluate Laplace of e raised to minus t into sin t divided by t. So in this problem we are going to use shifting theorem and division by t. So according to the situation we are going to decide which one is used to first and which one is useful. Okay, so according to the problem, first we should note something that is very easy, that is Laplace transform of sin t. As we have seen that Laplace of sin at is equal to a divided by a square plus a square. So here a is equal to 1, therefore Laplace of sin t is equal to 1 by a square plus 1. Now using divide by t property, we may write Laplace of sin t divided by t equal to integral s to infinity 1 over a square plus 1 ds. So integration of 1 over a square plus 1 is nothing but tan inverse s, and limits are s to infinity. So upper limit minus lower limit will have tan inverse infinity minus tan inverse s, and tan inverse infinity is nothing but pi by 2 minus tan inverse s as it is. So pi by 2 minus tan inverse s is nothing but cot inverse s. So this is the equation number 2, and now finally we are going to use shifting property. Therefore Laplace of sin t divided by t is nothing but cos inverse s by 2, and by shifting property Laplace of e raised to minus t into sin t divided by t is equal to cot inverse s plus 1, because here it is minus t and this s is replaced by s plus 1. So this is the shifting property. Now see Laplace transform of derivative. Laplace transform of derivatives. If Laplace of f of t is equal to f of s, then Laplace of f dash of t is equal to s into f of s minus f of 0. Here f of 0 is nothing but limit as t tends to 0 f of t. Here I have written f of 0. So this f of 0 is nothing but limit as t tends to 0 f of t. F of t is given to you here. Here it is f of t. So we are going to see the proof of this property. Laplace of f dash of t is equal to integral 0 to Laplace of f dash of t equal to integral 0 to infinity e raised to minus st into f dash of t dt. So this is by definition. So this line comes from definition of Laplace transform. Now we are going to use integration by parts to evaluate this integral. So e raised to minus st is first function and f dash of t is another, so second function. Therefore its integration is nothing but u into v. So e raised to minus st into integration of f dash of t is nothing but f of t here. So integral from 0 to infinity, that is limits, minus integral 0 to infinity derivative of e raised to minus st with respect to t is nothing but e raised to minus st into minus s. Now integral of f dash of t, which is f of t dt. So I have written here. Now if we substitute upper limit in the e raised to minus st, we have e raised to minus infinity, which is 0. So e raised to minus infinity into something with 0 minus lower limit e raised to minus 0 is nothing but 1 f of 0 here. So minus 1 into f of 0 for this one, minus into minus s, which is plus s into integral 0 to infinity e raised to minus st f of t dt. So remaining things as it is. Now in the next, Laplace of f dash of t is equal to minus f of 0 plus s into f of s, because integral from 0 to infinity e raised to minus st f of t dt is nothing but Laplace of f of t, but which is nothing but f of s. So Laplace of f dash of t is equal to minus Laplace of f dash of t is equal to minus f of 0 plus s into f of 0. Similarly, we can find another derivative. Laplace of second derivative of function t, function f of t is equal to s square into f of s minus s into f of 0 minus f dash of 0. Here f of 0 denotes limit as t tends to 0 f of t. F dash of 0 denotes limit as t tends to 0 f dash of t. Okay. So similarly for third derivative we may write Laplace of f triple dash of t is equal to s cube f of s minus s square f of 0 minus s f dash 0 minus s double dash 0. So here f of 0 denotes limit as t tends to 0 f of t. F dash of 0 denotes limit as t tends to 0 f dash of t, and f double dash of 0 denotes limit t tends to 0 f double dash of t. Okay. Now Laplace transform of integrals. So second property, Laplace transform of integrals. What is that? If Laplace of f of t is equal to f of s, then Laplace of integral 0 to t f of t dt is equal to f of s divided by s. Kindly see the statement of this property. If Laplace of f of t is equal to f of s, then Laplace of integral 0 to t f of t dt is equal to f of s divided by s. Okay. So we are going to see the proof of this property, and then will follow one question. Now let g of t is equal to 0 to integral 0 to t f of t dt. So g of t is nothing but the function t, which is nothing but the integral 0 to t f of t dt. Let me this equation as 1. Clearly g of t is equal to 0, because as t tends to 0, integral 0 to t f of t dt becomes 0, because upper limit so here lower limit is 0, and when t tends to 0, so upper limit will also 0. When limits of the integral coincides, then value of integral is 0, that we have studied in the previous years. So g of 0 is equal to 0, and if we take derivative with respect to t of equation 1, we will have g dash of t is equal to d by dt integral 0 to t f of t dt. So integration and derivative are the inverse to each other, so we may write integral, so integral and derivative are cancelled, so f of t and limits from 0 to t, so f of t upper limit, f of 0 is lower limit. So here f of t, if f of 0 is equal to 0, so we may take f of 0 is equal to 0, hence g dash of t is equal to f of t. We know that by Laplace transform of derivatives. Okay, so by Laplace transform of derivatives we may write Laplace of g dash of t equal to s into gs minus g of 0. Here g of 0 is equal to 0, so I have written here 0. So g dash of t is nothing but f of t. I have written here Laplace of f of t is equal to s into g of s. So g of s is nothing but Laplace of g of t, okay, minus 0. So f of s is nothing but Laplace of f of t, and s into Laplace of g of t. G of t is nothing but from equation 1, which is integral 0 to t f of t dt. So this proves that Laplace of integral 0 to t f of t dt is nothing but f of s divided by s. So I have transferred this s into LHS, so that I can write f of s divided by s is equal to Laplace of integral 0 to t f of t dt. Okay, so after these two important properties we may follow some example, in which first one is evaluate Laplace transform of integral 0 to t e raised to minus t sin t divided by t into dt. So clearly in this problem we are going to use three properties, because this is integral, this is exponential, that is shifting property, and this is division by t. So we are clearly using these three properties to solve this example. Now which one are these properties? So clearly these properties are shifting property, division by tree property, and then integral property. So for solution we may first note what is Laplace sin t. Okay, Laplace of sin t is nothing but 1 over a square plus 1 by division by t property. Okay, so Laplace of sin t by t is equal to integral s to infinity 1 over a square plus 1 ds is equal to tan inverse s, limit from s to infinity, and that is nothing but pi by 2 minus tan inverse s is equal to cot inverse s. So this problem is solved previous uh, time. So we may take cot inverse s is nothing but Laplace of sin t by t. Now by shifting property, so second property we will use is shifting property. So by shifting property, that will be, so this is nothing but f of s. Okay, so Laplace of e raised to minus t sin t divided by t is nothing but cos inverse s plus 1. So here it is s and here it is s plus 1 because e raised to minus t, so that we can write s plus 1 here. Okay, so in the next, by integral property, Laplace of integral 0 to t e raised to minus t sin t dt is nothing but cot inverse s plus 1 divided by s, because in this lecture we are having integral property, and integral property of Laplace of f of t is nothing but f of s divided by s. So this total thing e raised to minus t into sin t by t is nothing but f of t. Here we may consider f of t. So Laplace of this rounded term is nothing but cot inverse s plus 1 that we have seen in the um, we have seen. Okay, I would like to show. So this is nothing but f of t, and Laplace of f of t is nothing but f of s. So this is f of s. So we are having Laplace of integral 0 to t e raised to minus t sin t divided by t is nothing but cot inverse s plus 1 divided by s. Okay, so this is about the integral by t property. So along with this, I would like to stop here.